I wrote this title sort of after something that I read of Ken's. And I realized afterwards that there's a lot of other things that are closer, more related to zoos than what I'm going to be talking about. So I made some pictures of those things. But I thought, especially since we're not here together, that I'd just spend a minute or two introducing myself. And so let's see if I can figure out how to advance the slide. Okay, so there we go. So, so I like to think that we're placed somewhere. We're doing our mathematics from somewhere. So I'm in the Department of Mathematics, University of Arizona. For those of you that don't know where Arizona is, we're University of Arizona. We're in southern part of Arizona, way over here. We're about 2,200 miles from the Fields Institute. But this is really what you should think of when you think about Tucson. This is what Tucson looks like. These are our saguaro cactus. If you ever see any old Western movies, a lot of them were filmed out here. It's very beautiful, and it's a beautiful time of year. I'm the Director of Graduate Studies for Mathematics, so please send us your students to get PhDs. We'd love to have them. I couldn't help but make this little tidbit. So in 1995, I was an REU student at Cornell. I was working with Bob Strickartz, but two of the other instructors for that time were Carolee Bezdek and Bob Connolly. So I don't have a lot of direct connections to rigidity, but there is this sort of old. So my background, I come from the field of geometric analysis, Ricci flow, geometric flows. And you'll see that this talk and sort of my worldview kind of comes out of that background a lot. So I'm sure you'll sort of see that come out. And that's part of what I'd like to bring across as well. But I did start working in discrete differential geometry. And again, I view that often from a manifold perspective. So this is sort of a picture that generated on my lab of a ladybug on a tetrahedron, and this is sort of what the ladybug would see as it's looking in different directions. So I love that picture. Lately, I'm also very interested in geometry of data and geometry of machine learning. So this is a picture of the Stanford bunny that's gone through an autoencoder. If you know what that is, we're not going to talk about that here, but it's a sort of another nice, interesting way of looking at geometric objects. I've been fortunate to be funded, and a lot of the work I'm talking about was funded in various ways. In particular, part of a focused research group, and I wanted to just take a quick opportunity to advertise our workshop, which is going to be in less than a month. You'll see a lot of names that you might know, and names that come up or that are going to come up in this talk. So it's very exciting, and I think it'll be of interest to a lot of people here, and I hope you can make it. We're going to give some introductory talks for graduate students, so send graduate students as well that might be interested in the field. So this is the URL. Okay. So, all right. Thank you for that, and I'll get on to talk. So, as I mentioned, I like to view things from a Riemannian perspective. So, so I want to just remind you what conformality means in that perspective. So two Riemannian metrics on a manifold are conformal if they differ by a function. So I have a smooth function multiplied. So what that does is it changes the lengths of vectors, but it doesn't change the angles between the vectors. So that's this particular property. And we're going to be thinking of discrete conformal structures sort of from this idea. We might think of, instead of thinking of sort of two metrics being conformal, we can also think about a conformal deformation. So some sort of change through a family of conformal maps. And so what happens is you get a derivative. The change in the metric is just, again, multiplied by some function. Okay, so we're going to keep that in mind. And so one of the key things in Riemannian geometry related to conformal change is how does it affect curvature? So, so here is variation formula for the scalar curvature measure, which is the sort of the curvature that's closest to the sort of standard curvatures you might consider in the discrete setting. So the scalar curvature measure, if you change it by conformal deformation, you'll notice that you get the Laplacian of the deformation and you get the scalar curvature back. It's also notable that in dimension 2, this term isn't there. And we're mostly going to be I think we're going to be entirely looking at dimension 2 other than small comments here. It's a related fact, or maybe even a consequence of this, that the scalar curvature is the variation of a functional. So there's a functional whose gradient is the scalar curvature. In dimension bigger than or equal to 3, it's just the total scalar curvature, which is sometimes called the Einstein-Hilbert functional. Of course, that can't be that in dimension 2 because that's a topological invariant due to Gauss-Bonnet. And so you could ask, well, what is the functional? And one way is you can relate it to the determinant of Laplacian. So these sort of ideas are going to come up again. They're going to be developed independently, but I want you to sort of draw those connections as we move forward. And this is sort of the motivation. So I'm going to do something that I often, oh wait, I'm not ready for that yet. Sorry. So what's our discrete setting? So our discrete setting, we're going to mostly be looking, for most of this talk, I'm going to think about Euclidean structures. So what that means is I have a manifold, right? An abstract surface, triangulated, and then we're going to give it the structure of a piecewise Euclidean manifold. And so, so what that means, before I get there, what that means is that sort of each triangle is given some sort of Euclidean structure. And as is well known, certainly to this audience, one way to determine that Euclidean structure on each triangle is to assign edge lengths. So if we assign edge lengths to some sort of a positive number to each of the edges, that determines the Euclidean triangles, and then the geometry on each of the Euclidean triangles gives you Euclidean structure on the whole manifold. Under the assumption that the lengths satisfy the triangle inequality, that there actually is a triangle with those edge lengths. Yes. So that's sort of the structure, and we want to look at discrete conformal structures related to that discrete structure. And so, as I was starting to say before, I'm going to do something that I don't usually do, which is I'm going to start with the punchline to some extent at the beginning, which is I'm going to tell you what the axioms are for discrete conformal structures. Then we're going to move into examples to get an idea of why should these be the axioms. And then we're going to give an explicit parameterization of all discrete conformal structures that have these axioms. Okay, so that's sort of the direction we're going. So let me tell you about the axioms. The first one is that the lengths are determined by weights at the vertices. Okay, so this is similar to the idea in the Riemannian case that what I do is I take an inner product and I scale it at each vertex, but I can do it differently at each point. Okay, so if we think of vertices as points, we're going to allow deformation. So there might be some parameters that are fixed, but when I do a deformation, I'm going to allow weights to change at each vertex, but I'm not allowing them to change differently in different triangles at each vertex. Okay, so we have this function on the vertices that sort of determines the lengths, the edge lengths. Okay. Now, the next thing is there needs to be a dual structure. So the way we're going to get the dual structure is we take an edge length here, and then we cut it into two pieces. We assign one piece of it to one vertex and the other piece to the other vertex. And we sort of think of that as sort of a localization of the edge length. And then where these two meet, what we can do is we can draw perpendiculars. So these are all cut here. We draw perpendiculars. And what we would like is, so these perpendiculars make up part of the dual to an edge. And then we'd like to have a unique dual to the whole triangle, which would mean these three heights should, meet at one point. Well, that doesn't always happen, but it will happen under this constraint. So this is a constraint that tells you that these three heights meet at a single point. Okay, so we're going to make that one of our axioms that happens. So we get a dual structure so that we have sort of orthogonal duals to the edges. We have point duals to the vertices. And you can imagine we have sort of face duals to the vertices that are made up of sort of taking these triangles together and adding them all up. Okay, and then there's one third axiom, which is that if I take the length and I vary it by the weight at a vertex, then it changes by this partial edge length that comes from this. So over here, this is a picture of, should have switched the V and the W. This is what happens. So if I change FW here, it doesn't change this length based on the first condition, but it changes this, and it changes it in this particular way. We'll see where this comes from. It actually comes from Thurston's argument in his original circle packing work. Okay, so these are the three axioms that we're going to look at. And the next thing I'm going to do is look at other formulations of discrete conformal structures that fit into this framework. Okay, and the first one is going to be everyone's favorite one, which is the circle packing. At least at this conference, it's in the title. So circle packing. So just as a reminder, circle packing assigns lengths by just the sum of two radii. And I should mention, again, we're thinking of this circle packing metric as something that occurs on a manifold. So doesn't have to be in the plane where we have circles everywhere. Instead, I think of it as every triangle has these radii, and then we glue together the triangles sort of abstractly. And sometimes it's useful for those triangles to fit around in a flat way, and then we get a circle packing in the more usual sense. Okay, so this is sort of a circle packing metric. And so how does it fit into our framework? Well, of course, we take the lengths and we divide it up into this RV and RW. In order to get the variational form to work, we need to take the weights to not be the radii, but the log radii. And then so the partial edge lengths are the exponentials of the weights. And this log radius is something that comes up all the time. So this is maybe not surprising that that's an important piece. I also wanted to mention that the dual structure from this, if I take the dual, you actually get the dual to a triangle is the in-center, the center of the inscribed circle. And that's a very useful fact that partly because the in-center is always inside a triangle. And you'll see that some of the other structures that we're going to look at, that's not the case. And that can cause some difficulties. Okay, so I certainly don't want to give a whole history of circle packing, but I did want to bring up a few important pieces that are relevant to our discussion here. And so in particular, I wanted to mention Thurston's work. One of the small pieces in Thurston's work there is he shows that the radii determine the angles. And we call that local rigidity. So if I have a triangle, a single triangle, and I change, that comes from a circle packing, and I change one of the radii, it has to change the angles in a particular way. And the argument for why that's true is the motivation for that third condition. And we'll see even a little bit more about that. But that was a really important piece to the conformal structure of these things. So I wanted to mention, this also came up in some of the other talks, Colin de Verdier's work, and I really apologize for my French. I never learned any French, so I'm terrible with French names. But this is really important. So what he was able to show is find a functional for which the angle is the variation. And if you put that together, you can show that means the curvature is the variation of a functional. And the way that this comes about in this work is actually looking at the angle variation formula and noticing that if I use, remember F's are the log radius, if I use the log radius, then I get a symmetric, I get this symmetry. And because of that symmetry, I can integrate into a functional. And there's lots of other great work on these functionals that describe it explicitly by Springborn, Babenko, and others. And you can talk a lot about this functional, but this fact that sort of this angle, the symmetry of the angle variation leads to functional is very important. So John He actually calculated that angle variation and found this very interesting fact that the derivative of the angle at a vertex V with respect to the weight, which is, remember, the log radius at vertex W, it gives you the ratio of the in radius to the length of the edge connecting those two vertices. So this, I hope, reminds you of a conductance, sort of like if we take along that edge, we put a resistor in there, and that resistor, well, what is it? It's the conductance of it is inversely proportional to the length of it, and directly proportional to the cross-sectional area, which in this case is sort of the dual edge. I also had to mention Chow and Low, because if they hadn't started thinking about flow methods, I probably would have never ended up in this field in the first place, because that's what I was interested in. That's what I was doing as a graduate student. Okay, so there are other conformal structures I wanted to mention and fit into our framework. So another one is this one here. So I call this the multiplicative conformal structure, but some people just call this the discrete conformal structure. It looks a little bit more like the Riemannian case. Remember the Riemannian case? You took your metric and you just multiplied by a positive function, which you usually wrote as exponential of a function. And so what is this? Well, I fix an edge length, and then I take a weight at vertex V and a weight at vertex W, and I multiply them all together. So it's really, in a sense, looks a lot more like the Riemannian case. And so what happens? How does this fit into our framework? Well, what happens in this case is I divide up my lengths exactly in half. So I divide them exactly in half, and so these partial edge lengths are half the lengths, so these are the same. And if you look at the heights here, well, they're going to be perpendicular bisectors of all three edges, and so that gives you the circumcenter. Okay, so the dual to a vertex to a face is always going to be the circumcenter, and that, it turns out, has some nice properties, but also has some not so nice properties, in the sense that the circumcenter could be outside the triangle. Okay, that's not a major problem, but it's we'll see that it does come up as sort of an issue at times. Okay, I wanted to mention a little bit of history of this one. So it was the earliest I've seen it proposed was by the regicalculus literature. But I don't think this was particularly influential on these later works. I mentioned Feng Lo's work from 2003. He was also able to prove, again, this local rigidity, that if I change the weights a little bit, it's going to change the angles, right? Then there was work by Springborn, Schrader, Pinkel, and primarily Babenko, Pinkel, and Springborn, where they were able to take this local rigidity and look at a variational perspective. And there's an issue that pops up in the multiplicative structure that doesn't pop up in the circle packing, which is that if I start changing those edge weights, eventually I could violate the triangle inequality. And if I violate the triangle inequality, I don't know what angles are. And if I don't know what angles are, I can't build my functional. And so there's sort of this issue that comes up. That doesn't happen in the circle packing case. So one of the key things that happened here is they were able to extend the notion of angle to a place where the angles wouldn't normally be defined, and they're able to extend the functional in that way and still look at a convex optimization based on this sort of local rigidity. So that was a very important piece of mathematics. And then it was followed by another pretty interesting work down here by Gu, Lo, Sun, and Wu, where they combine this this notion of the functional together with having Delaunay flips. And so there's reasons that Delaunay, being Delaunay is important. It makes things better. It allows for uniqueness. And so there's sort of a process here that combines sort of this variational method as well as Delaunay flips to allow for a real interesting notion of discrete conformality. Okay, so there's one other type of packing that I wanted to, type of discrete conformal structure that I wanted to mention, which is inversive distance packings. So this is another one with circles, but what happens is I have my circles, so I have radii associated to each vertex, but they might not intersect. And so what I'm going to do is I'm going to fix the inversive distance between these two circles. So at any pairs of circles, they have an inversive distance, and I'm going to fix it. This was, I'm pretty sure I have the history here right, but there might be people that can correct me if I'm wrong. I think it was introduced first by Bowers and Stevenson in 2004. Renguo proved a local rigidity result for these in certain cases. To be a little bit careful about what inversive distances are allowed. So Feng Lo proved the global rigidity, again with this sort of extending the angle structures to a convex functional, and Xu Xu sort of extended that to a larger class. And I should mention, I probably should mention that you can also sort of fit circles with a fixed intersection angle. So if there's an intersection, the inversive distance is essentially that intersection. And so, so circles with fixed intersections. I probably should have put that in here, which was studied by Thurston and a lot of people previously. Okay. So, oh, and this is, of course, a picture of my favorite inversive distance circle packer. Okay. Okay, so let's get back to the general case. In terms of the general case, you know, where does it come from? And where it comes from is angle variation formula. So at the end of the day, we'd like to have an angle variation. And so this is what we found. So this condition, this one that was the most mysterious of the three, where it comes in is looking at angle variation. Okay. And so if we have a variation of lengths that satisfy this particular property, then we can calculate the angle variation. So the derivative, and I didn't put the angle here, but so what we're doing is we're taking a weight here at W and an angle here at V, and we look at the change in this angle as we change this weight. And what we get is something very similar. That's my next result here. The generalization of John Hu's result in circle packing, which just says that what you get is the ratio of this dual height to the length. Okay, in any case, all these cases. And I should mention, and I'll have some pictures later that have the circle outside. This H is assigned height. So if the circle happens to be outside over here, we take a negative, and that reflects the fact that if we change this weight, then the angle is going to be decreasing instead of increasing. But that's okay. All that sort of works fine in this setting. And I also wanted to point out that with our other assumptions, where we assumed showing that these three heights meet at a point, that ensures that this HVW, right, is sort of symmetric. And so this is symmetric. And so I think I'm going to say it on a future slide, but I'll tell you anyway. Right, this symmetry allows you to write down functional, right, whose derivative is the angles. So that's important a fact that follows from this particular calculation. Okay. So I'm not going to go through the proof, but I do really like the picture. And so I wanted to just explain just briefly that condition that I just showed you. What it does is it ensures that if I vary the weight in W and I look at the center, right, that comes from this height here, the center, what happens is that condition ensures that the new vertex and the old vertex in the center are on a straight line here. I get a straight line, and then what I find is I get sort of these similar triangles. And the similar triangles are exactly what allow you to show that the variation, get that variation formula. And there's a picture here of what happens if the center's outside. Again, we get that the center and the vertex and the new old vertex, new vertex are on a line. And so again, we get sort of similar triangles. And you have to just keep track of the signs. So, okay, so that's where this came from. And so, of course, it follows from the same construction that you can give a variational formula. And just from integrating that form. Of course, there's other questions about what is that functional, and it turns out it's related in most settings, I would like to say, certainly in a lot of settings, to various hyperbolic volumes. Okay, I'm not going to get into that here, but that's a very interesting course circle of ideas that's very important to this theory. The other thing I wanted to point out is if we look at a triangulation and we think about the curvature here as 2 pi minus the sum of the angles at a vertex. So at a curvature at a vertex, I add up all the angles, I subtract it from 2 pi so that it's 0 exactly if the triangles fit down. So if I take a conformal variation here, what I get is the curvature changes by minus the Laplacian of u, which is almost exactly the same formula that I got, well, that I showed you anyway, in the Riemannian case. So it's a very close connection to the Riemannian when we consider this curvature look as r times the area measure. And there's lots of, I should mention, there's lots of work of Cheeger and others relating those curvatures in other ways, the discrete curvature to this curvature measure. So this Laplacian, what does it look like? It looks sort of like a graph Laplacian. And again, it has this property of you have a dual length to a length. So it looks like a conductance in a traditional way. The dual length is just the distance, sign distance between these two centers. And you actually get it by just taking the sum of the height here and the height here. And so sometimes that could be negative. And if that's negative, we get into some interesting cases because, so if this is positive, then there's lots of theory of weighted Laplacians on graphs that follows through. You get maximum principle and things like that. If not, there's some interesting questions because it still, in some sense, has this kind of moral, sort of morally positive, but not actually positive. So you have to look more carefully at the operator. And you can I'll show you a little bit about that later, but it's a really interesting theory. And one of the reasons that it's a little bit different than typical numerical analysis in some cases. Okay, so I talked about that, and I should mention, so what kind of Laplacian is this? Do we see this before? Well, it's actually a finite volume Laplacian. So what that means is you have sort of these control volumes, and the control volume for this is here. Sort of this, it goes all around. Consider that as control volumes. You look at piecewise constant functions, and you do a sort of a variational look at the Dirichlet energy, and carefully you get exactly this Laplacian. It turns out in dimension 2, in a certain case, in fact, it's the multiplicative, the one that comes up in the multiplicative conformal structure, you actually have the finite element Laplacian. That's only going to be true in dimension 2. But it's an interesting fact that again was known in the numerical analysis, that this particular finite volume Laplacian that comes from perpendicular bisectors is the same as the finite element Laplacian. But having the finite element Laplacian, right, that gives you a lot of power because you can look at, for instance, the Dirichlet energy restricted to the finite element space, and that tells you a lot, which we don't have in most of the cases. Okay. Anyway, it's important so you note that sort of this variation of the curvature comes from the Laplacian. Okay. So All right, so the real result here is that we can write these out explicitly. So that is older. This is a little bit newer. This is work with my my graduate student, my former graduate student, Joe Thomas. So I've rewritten here the axioms for discrete conformal structures. If you're a little bit, if you're following very closely, you'll notice I changed something here. I said that the partial edge lengths depend on F and W, not the lengths, but with 3, I can interchangeably, I can change those out. It's not a problem. So these are the 3 axioms that I gave before. And it turns out that under those axioms, we get exactly this structure. So I can always write the square of the edge lengths. I fix parameters alpha and eta. And then I just get this formula here where I'm going to allow the F's, the FVs and the FWs to vary, but the alphas and the etas are fixed. Okay, this is all that you can have if you have these 3 axioms satisfied. Okay, and I just wrote down the length, but using 3, I can now calculate the partial edge lengths and everything else. I should also mention that, you know, there's sort of an invariance, so I can always shift the values. So this alpha is associated to a vertex. This weight F is associated to a vertex. So I can always shift this to make the alpha be in either -1, 0, or 1. And this structure, why is it? One of the reasons I think this is interesting is this structure has been seen before. It's been known, it's been observed, or something close to this has been observed to encapsulate circle packing, multiplicative, and other structures. One of the interesting things is it comes directly from the axioms. But these have been studied before, and I should mention, well, this paper here by Zhang et al. They looked at these structures in detail, and also hyperbolic case. I'll talk a little bit about hyperbolic at the end because we have a similar theorem. And then I should mention that there's lots of relationships of these sort of structures to hyperbolic volumes. Okay, so this is the key result here. And I'm going to give you, the proof is not hard once you sort of know what you're looking for. So I'm actually going to sort of outline the proof. So remember, these are the assumptions. This is what we're trying to find, is that the lengths are here. So there's a couple of sort of basic observations. So the first thing is that this condition down here implies a symmetry of the derivatives of the partial edges. So this dvw respect to fw, well, this is the derivative of the length with respect to v. And so I get this sort of mixed partial. And so that allows me to get this sort of symmetry in these derivatives. And that symmetry tells me that if I take the derivative in this direction of VW, I get VW back. I'm going to use that to actually look at something slightly different, which is this dVW squared minus dWV squared. So it's sort of the symmetry, the lack of symmetry between the V and the W on the partial edge lengths. And if I take it in this particular direction, again, I get a similar formula. I get the same thing. So I'm almost there. Why do I care about this particular, why is this particular quantity useful? Well, it's useful for this reason. If I write down that quantity and I use condition 2 here, I can write it here. And if I look at that carefully, and I think about condition 1, I see that each of these terms, it depends on FV or FW, but not both. So since it doesn't depend on both, if I differentiate it with respect to each, I get 0. So I get this condition is equal to 0, and I can use this together with this previous one to, so I just take this, I differentiate it, say, with respect to FV on both sides, and the mixed term goes away. And so what I get is this condition, this equation right here, which now I can integrate, right? Because you see the exponential right here, it's just the derivative of FV of this, okay? So I integrate that, I get the exponential, and then I have to work back and forth a little bit. And at the end of the day, I get this conclusion. So you can see that it follows primarily from sort of this, the way that this is put together, and the fact that the interaction between this constraint with the fact that the partial edge lengths only depend on certain weights. Okay. So what's nice about these? Well, we can ask about the local rigidity. So you remember I had local rigidity results for by a number of people for different situations like circle packing and multiplicative. What is the case in this more general form? And it turns out that you can look at sort of one sort of theorem you can prove on local rigidity has to do with where the center is. So it turns out that if the center of each triangle is, so it's easy, relatively easy to see if the center is inside the triangle itself, but actually it only has to be inside the circumcircle. So if it's inside the circumcircle, then you get rigidity in the sense that for a single triangle, if I change a vertex weight, I have to change the angle. Okay? And this follows from, this is sort of a Laplacian, remember the derivative of the angles is basically the Laplacian matrix for that triangle. So this has to do with the Laplacian determinant formula. And this result, it's sort of another interesting connection to rigidity. The way that I came across this result was I was looking, I was trying to understand this Laplace determinant, and I was at a conference at Oberwolfach, and I think it was on the bus back, I was talking with Walter Whiteley and asked him if he knew or had some idea. And what he did is he coded something up in GeoGebra and experimentally found that this circumcircle was the relevant thing, which I had no idea. Neither of us had any idea. And then, of course, once we found that, of course, it's related to some classical theorem in geometry, which it is. But it's a nice result, and it's a nice thing that's come out of collaboration between circle packing and rigidity in a very nice way. So I should mention that this condition here, that the center is inside the circumcircle, well, of course, it's true for circle packing, because it's true for any time that the centers are inside the triangle. And it's also true for the multiplicative one. In the multiplicative one, the center is the circumcenter. So in fact, it's always at the center of this circumcircle, which in some sense is a very good condition, although I haven't figured out how to use it, how to show in what sense that's a really, really good condition, but it feels like it should be. In some sense, the best possible choice. Okay, another way that you can get rigidity is with sort of a weighted Delaunay condition. So this is a single triangle, but if I'm looking at multiple triangles, I can look at the dual edge length. And it turns out all I really need, so I don't absolutely need this, but if I have that the dual edges have positive length, there's no negativity, that's equivalent to being weighted Delaunay in the appropriate sense. And then you get a Laplacian with weights, with positive weights, and so you have maximum principle, and you get rigidity sort of for free. So the difficult cases are the ones where you don't have that. Yeah, okay. The one of the things that's not great about this formulation is that for most cases, we don't know how it's related to our choices, our original choice of discrete conformal structure. So in the multiplicative case, in the circle packing case, they just say it's multiplicative or it's circle packing, and it's automatically satisfied. But in most cases, I don't know how to do that. I don't know how to make sense out of that. So so and same thing sort of with weighted Delaunay. These are conditions that are sort of hard to check. So then I wanted to say a few words about very recent work by Xu, preprint that just came out, that treats this case and finds a big class of these sort of discrete conformal structures for which there is both local and global rigidity, again, using this sort of methods of Bobenko and Pinkel and Springborn to extend angles into a convex functional. And so I'm not going to talk too much about this, but look at these alphas being 0 and 1, and then you have these two conditions that you need. And once you have those, he's able to show that you actually have both local and global rigidity, which were both not known previously for the sort of most general case. And these conditions here cover the main cases that we're interested in, which is circle packing, multiplicative, and certain inversive distance circle packings. So this is nice, and I'm hoping I get to hear a lot more about this, either talking to Xu at this conference, or he's also going to be speaking at our conference in May. Okay, so why am I interested in these different conformal structures? What's so nice about having this all in its own sort of place? Well, one thing is it gives flexibility. So I can take this triangulation, and one thing I could do if I wanted to redraw this in a nice way is to circle pack it. So I give it some sort of circle packing idea, and right. So I have these circle packing, and I'm shifting right now into a second part of my talk without specifically telling you. We're going to talk a lot now about domains with boundary. Okay, so this is a domain with boundary, and so the sort of classical circle packing, you pack the boundary circles to be interiorly tangent, and then all the other ones are tangent. And I'm taking this sort of manifold circle packing and making it into what I would call flat circle packing, or you might call more traditional circle packing. If the curvatures are all 0, I can draw this out. I think Ed Crane mentioned the monodromy theorem in his talk. That's exactly what you need to go from the metric to the drawing. But we might have other things we might want to do. Maybe we want to do circle packings, but instead of having these boundaries internally tangent, maybe I want them to be orthogonal to the unit disk. That gives me something that looks a little bit different. It fills out the disk in a different sort of way than this does, and that might be nice. I should mention that this sort of structure has been studied. It was studied in particular by Bowers and Stevenson from well, I should say both of these cases, the typical way that one would study them is to look at the hyperbolic case. In fact, Ed Crane gave a really good explanation of this yesterday. The fact that you can turn this into hyperbolic triangles, there's circles, they're still circles, and then you can think of these as horocycles, just circles with infinite radius, makes this a really nice way to do things in a sense. And this is also similar, except these now are geodesics, right? If you're doing them in hyperbolic space. But maybe I don't want to do them in hyperbolic. I want to do Euclidean. I just would like to possibly do Euclidean because maybe I have a different structure or some other reason that I'd like to do things Euclidean. So I'm going to tell you about how to use this zoo to formulate this as a Euclidean problem, which is maybe not as well posed, but well, it's well posed. It's just maybe not as good a problem in certain ways, but is in fact Euclidean nonetheless. Okay, so what if I want to do multiplicative? What's the corresponding thing multiplicative? And it turns out that it's very natural to require that the boundary is on the unit disk. So that's a very natural condition, and that's the one that we will do. We will formulate in this one. Okay, so let me show you these examples a little bit more. Oh, before I show you the examples, let me show you what the method is. Okay, so as I mentioned, I would like to do things Euclidean if at all possible. So So what am I going to do? Well, what I'm going to do is I'm going to take each of these boundary vertices and I'm going to attach them to a new vertex, which I call the augmented vertex. Okay, so all the boundaries. So for each boundary edge here, I'm going to have a new triangle that comes from, I should show this one, a new triangle, right, that comes from this edge, boundary edge, and then two edges that go to this auxiliary vertex. And now what I want to do is I want to force these things not to become, so as a Riemannian geometry, the first thing I would think of is I want to make this into a sphere, right? But that's not quite what I want to do. What I actually want to do is I want to make this into a doubly covered disk. So what I want is for this augmented vertex to want to push this down into a nice disk that's enforcing some sort of boundary condition on the rest of this. And then the interior is sort of the typical sort of curvature equals zero condition. Okay, and that's sort of the difficulty. What I didn't mention is there's other kinds of boundary conditions that are very natural to these functionals, like specifying angles, angles on the boundary and things like that. But this condition here, this condition is not of that type. It's not as clear how to do that. So this is what we're doing. We have sort of this doubly two pieces that are kind of pushing and pushing. And so what I want is the curvatures to be zero here, the curvatures to be zero here. And on the boundary, what I want is for the angles to add up so that they fold over exactly. Okay. And, there's interesting ways you can formulate this in my paper, but that's the basic idea. Okay. And so what does this look like for circle packing? Okay. So circle packing, so remember, this is what the structure is. And so we just take the usual circle packing for the interior, for all of these vertices, right? Which is alpha is 1 and eta is 1. And then we have the augmented vertex. And then what I do is I stick with alpha equals 1, but I make the new, the edge weights -1 actually. And what does that do? Well, what the -1 does is it makes this edge length between v and v hat, it's equal to the difference between the radius for v hat and the radius for v. So I'm taking this radius minus this radius, and this radius minus this radius, and that sort of enforces exactly what we want. But these triangles come from these circles. Okay. But what if we want to do circles orthogonal to the boundary, with circle packings? Again, what we can do is we do the same thing on the inside, but instead what we do is we make this eta here 0. And that sort of essentially tells us that the intersection angles is pi over 2. And so for the augmented vertex, it sort of looks like this circle and this circle are orthogonal to the circle for v. And what if we wanted to do the inscribed? So in this case, we're in the multiplicative structure. So the multiplicative structure, these etas are related to that original length that I described. I have this 2 in here, so you have to be a little bit careful. And then these alphas are 0. So it doesn't have any piece like this. It's multiplicative entirely, just this piece. And so what do I do on the boundary? Well, actually, all I have to do is assign the alpha 0 here. And remember that the alpha here is 0 already, right? So the eta 0, the alpha 0. And so all I get is the same thing for every edge. I don't know why I wrote 1 here. It could be whatever you choose, but it's going to be fixed, right? It's going to be the same. And so again, you have a circle. It's going to push this to be interiorly inscribed in the circle. Okay. The one last thing I wanted to mention is these pictures. How are these pictures made? They were made exactly by doing this process that I mentioned. So I have conditions for each of these vertices, curvature equals 0, and then on the boundary I have this curvature turned over. which is also a type of curvature. And then you're trying to find all those curvatures 0. And I used a flow of these that is not exactly a gradient flow. And I'm not exactly sure why it works. But it does seem to converge to nice pictures here in many cases. And then we used monodromy to draw them. So, okay. Just in the last couple of minutes, I wanted to say a few words about hyperbolic background, because in some sense, that's really the most exciting, but it's a little bit harder to talk about. So most of this work that I've talked about here has analogs in hyperbolic geometry and that are proved. So what is the discrete conformal structure in hyperbolic background? So these 3 axioms. So it's pretty similar. Again, we want to assume the vertex deformation, that things are just changing by the vertex. Again, we want to have an orthogonal dual structure. So again, we're going to take the lengths and we're going to cut them. But in hyperbolic geometry, so I want this to be a hyperbolic triangle. You might ask, well, what's the condition for these heights to come together at one point? That's going to be different than the Euclidean case. And it turns out that this is the condition. It's a pretty nice looking condition. And one of the interesting things about this condition is it allows for these centers, sort of a generalized center that might not live inside hyperbolic space. So this picture here, schematic, it's a schematic. But if you think of this as the Klein model, so these are all right angles. But you could have a center that's inside hyperbolic space, which is just like the Euclidean case I talked about. But it's possible that you have these edge lengths that satisfy this condition. And what happens is, as I do my heights, they come out and they go off to infinity and they never intersect in the hyperbolic plane. But what happens is in the generalized sense, they do come together. There's a meaning for these things coming together. And that's also encapsulated in here. So there's sort of a notion of a generalized center of these hyperbolic, certain classes of hyperbolic triangles. That's very interesting. And so this allows for any of those, actually. And then we have this length variation formula, and the length variation, you want this to be hyperbolic tangent of the partial edge length. Okay, so these are the 3 axioms for hyperbolic background. And then what can we prove about those axioms? And this was in the same paper. So this was new as well. You have angle variation formulas. So you can write down the angle variation formulas, and they sort of look like the HVW divided by LVW. There's a term, there's a tanh or a sinh here, and then there's this other term here, this cosh dVW that comes up. So it's sort of similar, but not quite as nice, at least the way I've written it here. And I wrote the diagonal one. I didn't mention this, but in the Euclidean case, it's easy to calculate the diagonal one using the symmetry and the fact that the sum of the angles is equal to pi on Euclidean triangle. So for hyperbolic, you have to work a little bit harder. You have to calculate the derivative of the area, but that's not particularly hard. Okay, and there's this funny beta that has to do with whether the center is sort of inside hyperbolic space or outside hyperbolic space. And so you have to sort of make a little bit of an adjustment. And there's also a way to think about this if the center is on the sphere at infinity. And this, so sort of similar the structure or same structure under a little bit of a different guise was looked at sort of independently, actually, but by Zhang and these other collaborators. And they have a lot of interesting stuff in that paper. You might be worried that this is not symmetric, because it's not anymore, because I have this dVW, which is not the same as dWV. So you might say, uh-oh, my other one, at least it was symmetric, it's variational formulation. It's broken, I don't have variational formulation. But it turns out that there's sort of a symmetry. If I change this f to another parameter, then I can sort of get rid of this and I can find a variational formulation. It's not, F is not quite the right parameter. So I'm not going to write down the parameter, but, and it's easy to see using the second theorem, which gives the general formula for the edge, the length. So this is the general formula proven similarly to the Euclidean case of what do all the lengths look like. Again, we have these alphas fixed, we have these etas fixed, and then the f's change. And this, it's interesting, these were formulated, so there's a hyperbolic discrete conformal structure by Babenko, Pinkel, and Springborn in 2015 that was motivated in an entirely different way. And again, this other group, they don't look quite the same, but they're equivalent. Turns out they're exactly equivalent. So these are the only ones that you can have if you satisfy those three axioms. So, okay, I'm running over, but I just wanted to I like to end in future thinking about stuff. So what's not known? General existence theory. In a lot of cases, it's not known, right? Can I pack this circle? We have a notion of what it means, but does it exist? When do we know it exists? I'm really interested in convergence to smooth maps. There's some really interesting recent results of Qianqi Wu and Feng Lo and their group on that. We have some other stuff we're working on, convergence to smooth maps. Very interesting direction. Higher dimensions. There's some interesting stuff in dimension 3. I have some angle variation results. There's some work of Babenko and Izmestiev and some of Izmestiev's other collaborators, Philosopher, looking at sort of 3D structures. Very interesting. I mentioned the Laplacian, things about the Laplacian. There's also been some really interesting work recently where they don't assume orthogonal duals. And I don't know how that's related to circle packing, but it's an interesting area of its own right of discrete differential geometry. And then just in general, new computational tools. I told you I had this flow that seems to work sometimes. I don't know why. It's not convex. You know, what can we do future? That's sort of the last thing that I want to leave you with. And thank you.
Thank you. Very great, interesting talk. Let's thank our speaker. Yep. And then why don't we take a couple of questions? Ed?
So you mentioned that this center could sometimes be outside the hyperbolic plane, CUV, and then you hinted by saying it was space-like. Does that mean it's really a point on the other hyperboloid in the hyperboloid model?
Well, it depends how you want to think about it. The way I like to think about all this is living inside the Minkowski space. And so if you think of it in that sense, it's going to be off. It's going to be, so you could think of it as, you know, you could recenter it maybe to be on that other hyperboloid, but.
So does that mean it really corresponds to a geodesic or a codimension 1 hyperplane?
Yeah, that's right. That should be one way to interpret it for sure. Well, and you can sort of see it, right? I mean, I have a bigger one, don't I? Sorry. Yeah, so you can always, when these things happen, there's a geodesic that's orthogonal to all three. So that's another way to formulate this, is that you have a geodesic that's orthogonal. That's equivalent to having sort of a center. This sort of feels more like a center to me, but from a strictly hyperbolic situation, you have this. And if you want to try to relate this to like hyperbolic volumes of generalized hyperbolic tetrahedra, then that's exactly what you need. Yeah, you need to be thinking of it in that way.
Any other questions?
I have a naive question. I must be misunderstanding something. when you had this picture of the triangulation inside the circle and you had a double cover around the outside, remember that? I don't understand, isn't there a topological obstruction to doing that?
I'm not sure I understand.
You know, you have your picture of the triangulation where the vertices are on the circle on the outside. Yeah, this one.
Uh-huh.
Right. And you wanted to have a double cover around the outside? So
Well,
it's like you attach a cone where it wraps around twice. I don't quite understand how you can extend it to the inside. You need don't you need another double cover on the inside?
yeah, so this is one cover. The other cover is just a cone. It's just the cone.
No, I understand that, but you said there was a double cover of that cone around the outside. I must have misunderstood.
No, there's not a double cover. It just sort of folds over.
Oh, okay.
Just folds over. So the idea is that this cone is enforcing a certain boundary condition through tension.
Yeah.
Yeah, there's nothing double. It's very simple formulation.
Is there a way that you can flow the choice of what you mean by discrete conformal structure? So somehow choose one set of data, but then vary your choice of the alphas and etas?
Now that's a very interesting question, and I haven't seen it looked into at all. But I think that's a really interesting question, especially if you want to use some sort of continuity to prove. To prove, there's lots of really great tools in circle packing and some of these discrete multiplicative structures and things like that. And it'd be very interesting to be able to apply those to other structures that are not those. And things like the ring lemma, right? The ring lemma is a big one. And there's a version of the ring lemma for the multiplicative structure, but it's not clear if there's one sort of in between. And so, yes, I think that would be very interesting. In fact, I have a student that's looking at exactly that, but we haven't gotten anywhere yet. But I think that's one of the nice things about this sort of formulation is you should be able to do that. Look at that kind of a change. But as far as I know, I don't know of any work that's actually done that.
So how do you compute your packings? Do you have your own algorithms, or on what they are based?
Yeah, so the typical thing that I do, and I don't know why this works exactly. I have so it's basically the combinatorial Ricci flow, which is right. You take the derivative of the weights is equal to minus the curvature. Mm-hmm. But you define the curvature at the boundary as the difference between the angles on the top part and the angles on the bottom. And then I think you move the radius, the weight of the central piece in the opposite direction. And that usually works.
And so you go through the packing step by step, vertex by vertex, or do you do it globally?
I do it globally.
Globally.
Just run a differential equation and hope it converges to zero, which the curvatures converge to zero, which it often does. But I wouldn't say that I've done enough work to say that it almost always does.
Thanks.
I'd be really interested though to know like when that works, how often it works, and if there's a better way.